Let's say we have a big circuit here, and what's attached to that circuit is a load that you can adjust the value of it. So when you see a line going through that, that's called variable resistor. You can change the value of that resistor. R sub, yeah, exactly. So we're looking for what is R sub L? What value can I put there that will maximize my power transfer to that load, that resistor? Well, we know I can take this circuit and replace it with the Norton or Thevenin equivalent, right? So I can cut this circuit there and replace it with the Thevenin equivalent, and that's V Thevenin, R Thevenin, and this is my R sub L. This is where I cut it. And I'll go through that and try to derive what the maximum power transfer to the load will be. Well, the power, we know the power is calculated by doing what? Voltage times current. Or you can use what? V squared over R. Or it can be what? I squared times R. So if I want R sub L to have maximum power transfer to it, P R sub L, let's calculate the power to R sub L, is going to be the voltage across this one, we'll call it VL. It's that voltage squared divided by what? R sub L. Whatever the voltage right here divided by that resistor. And I can find VL by doing what? Isn't that voltage division? So it's V Thevenin times R sub L over what? The sum of them, R sub L plus R Thevenin. So the power transfer to that load, the power, instead of VL, I'm going to write the equivalent, which is what? V Thevenin times R sub L divided by R sub L plus R Thevenin squared divided by R sub L. Dividing by R sub L the same as multiplying by 1 over R sub L. That'll make the math easier. That's V Thevenin squared, RL squared over RL plus R Thevenin squared times 1 over R sub L. And notice this R sub L will cancel one of these, so the power to the load, it's always going to be V Thevenin squared times R sub L, because that will cancel one of these, over R sub L plus R Thevenin squared. Keep in mind R Thevenin is a constant value, V Thevenin is a constant value. The only thing that's changing is R sub L. Now the topic for us is maximum power transfer. This is the power transfer to the load. I'll wait till you finish writing. This is the power delivered to the load. If you want to maximize it, what do you need to do? Think of calculus.
Yeah. It's like a Weisman problem type thing.
If you, the second derivative has to be equal to 0? Yes.
Well, take the first derivative and set it equal to 0. Second derivative equals 0, that's inflection point. First derivative is min-max point. So you need to find the derivative of that. And the derivative has to be with respect to R sub L, because that's the only thing that's changing. These are constant. R Thevenin is like a 5. This is like a 20. So let's find the derivative and set it equal to 0. with respect to R sub L. So this is a constant, so leave it alone. And to take the derivative of this, we have to use the quotient rule. That's a fraction. So if you remember your quotient rule, it's the bottom times the derivative of the top. And what's the derivative of R sub L? I'm doing with respect to R sub L. Isn't that a 1? Minus the top times the derivative of the bottom. The derivative of this, we have to use the extended power rule, which is what? 2 times what's inside the parentheses to the power of 1 times the derivative of what's on the inside of that, which is a 1. Again, our Thevenin is a constant. The derivative of any constant is 0. Over the bottom squared. So when you square the power of 2, it becomes the power of 4. Power of 1 here. Because it was 2, right? You take 1 from it, then you multiply by the derivative of what's on the inside. What I could do here is factor out RL plus R Thevenin from each one of them. So if I factor RL plus R Thevenin from each one, what's left in this one? It's one of these still. And this will be 2 times R sub L. Now, this can cancel one of these. There's 4 of them in the bottom, 1 on the top. This will cancel one of these, making it 3. So the derivative of that, it's V Thevenin squared times R sub Thevenin minus R sub L over RL plus R Thevenin cubed. That's the derivative. And if you want to maximize it, you want to set it equal to what? 0. That's how you maximize anything. You take the derivative and set it equal to 0. That's your possible min or max. Well, when you have a fraction, for the fraction to be 0, that means what? The top has to be 0. V Thevenin is not 0, so the only way the top will be 0 if what? If R Thevenin minus R sub L is equal to 0, which means R sub L has to equal R Thevenin. So that's the rule for maximum power transfer. So for maximum power transfer, you will need RL to equal R Thevenin. That's what you need to have. So if the problem says, tell me what value of load resistor I can put there, make sure that value has to equal to R Thevenin. If it is, you'll have a maximum power. Why? Because the voltage now will be half of that, and V squared over R, that'll be your maximum power. So if that's the case, then, well, then what is the voltage going to be? Remember, if these resistors are equal, what's VL is going to be? Half of that number, right? Because they are equal resistor. So then in that case, VL will be V Thevenin divided by 2. So if I plug it in into this equation, what is then the power transfer to the load? Instead of VL, let's write V Thevenin over 2, square it, divided by R sub L, and your final answer is going to be what? V Thevenin squared over what? 4 times R sub L. That's how much power will be sent to the load. So the amount of power delivered to the load is going to be V squared, or V Thevenin squared, divided by 4 times R sub L. Ooh. Our book does all this derivation in one step. So, but this is the math behind it, the calculus behind it. That's where it came from. Let's take a quick example. And we have 2.5. I think it's 2.5 here. Okay. Yep. Here's the example. We have 2.5 sine 440 t millivolts. 2.5 sine 440 t millivolts. This number represents what? 2 pi f. So if you divide it by 2 pi, that tells you what the frequency is. It's a source here. It's an AC source. It's not a DC value. It's changing. It's a sine wave. We have a resistor on the top of 300. We have 17K right here. So that's a large value. The top is just 300. This is 17K. This is 5K. This voltage plus to minus VG. Now, this is a current source with a value of 0.03 VG. A resistor here of a value of 1K. And there's my load resistor. R sub L, again, which is adjustable. And the question, what value can I put in there for R sub L to maximize my power? Down the road, you'll learn about something called transistor, NPN, PNP transistor. This is actually what the equivalent of that transistor. We don't have to know that here. So we're going to cut this circuit here. We're going to Thevenize it. And notice you have independent and dependent sources. So you need V open circuit, you need I short circuit, because R Thevenin is going to be V open circuit over I short circuit. And V Thevenin is equal to V open circuit. So I need both of these before I can move forward with it. Here's my V. Okay, I was going worse. What happened to my value there? So let's look at it. Let's find V open circuit. Let's find V I short circuit and do the math. 2.5 sine 440 T, that's millivolts here. 300 By the way, if I combine these two resistors, would that change VG? No. Let's combine them into one. Oh. Here's my eraser here. Nothing here. .03 VG. (1K), and V open circuit is right there, plus to minus V open circuit. This .03G, where is it coming from? There's nothing coming from this end. That's an open end here. So that current is actually coming from up here. It's coming up there and it's continuing to go in this direction down this way. So this voltage here, because the current is going up, is going to be marked what? Plus to minus. So I can see V open circuit, just looking at that picture, is going to be what? Negative .03 VG times 1K. If I know what VG is, I'm done. Can I find VG? Well, that's voltage division. If you do voltage division, what are you going to have? VG is equal to what? Oh, I forgot to find the value of that resistor.
So it's up there,
Huh?
is it 5K?
Well, 5K and 17K in parallel, right?
Oh, that's right.
4.77.
Is it? 4.77K? It's the product over the sum.
Yeah.
5 times 17 over 22. 3.8. 3.864.
Oh, 5? Wait, what? I thought it was. Oh,
5 and 17. The product over the sum. So you were wrong there.
I did 15 times 7.
Dead for life.
I just woke up like 1.
3.864 basically. That's fine. K. I'll go 4 here. Of 4. 3.864. So what is VG is going to be? 2.5 sine 440t millivolts, times that resistor, which is what? 3.864K over the sum of them, this plus that. 3.864K plus 300. The K will cancel the milli. Times the 2.5. I came up with VG here, which is 0.0023 sine 440t volts. The millis are gone. Yep, the millis are gone. And now to find what V open circuit, multiplied by that, what's V open circuit going to be? Times a negative 0.03 times the 1,000. And if everything is good, I got negative 0.0696 sine 440t. Now I need to find I short circuit, because I got to find R Thevenin. So that's V open circuit. Let's look at I short circuit. Let's put a wire there. Well, once you put a wire, what's going to happen to that resistor? I'll put the wire first. .863 I said, or 4, what was it? 4. .03 VG. When you put a wire here, short circuit, what's going to happen to that 1K resistor? It's gone. I need to define the current this way, I short circuit. Because I define V open circuit top to bottom, I short circuit's coming down. Well, the good news is that VG here did not change, because this is still 2.5 sine 440t millivolts. So VG never changed. Still voltage division. Times 3.864K over 3.864K plus 300. So VG is still 0.0023 sine 440t. Do we know what I short circuit? Well, let's look at this current. This current, where is it coming from? Coming from here, which is coming up from here. So what is I short circuit? It's negative 0.03 VG. So take that number, multiply by negative 0.03. 0.0023 times 0.03, 6.9 times 10 to the negative 5 sine 440t. 10 to the minus 5. So what is R Thevenin? It's V open circuit over I short circuit. V open circuit, if I remember, negative 0.0696 sine 440t. I short circuit, negative 6.9 times 10 to the negative 5th sine 440t. These guys will cancel each other out. Do the math. Negative over negative is positive. 1,000, what do you know? On the money. Right there. So 1,000. So that means R sub L for maximum power transfer should be 1,000 ohm. R Thevenin. And what's the voltage? The maximum power. Remember, we did the math. It's V Thevenin squared divided by 4 times R sub L, right? So maximum power, max power is going to be V Thevenin squared divided by 4 times R sub L. And you tell me what is V Thevenin? I lost it. Here we go. I got it now. Negative 0.0696 sine 440t squared divided by 4 times R sub L. That's 4 times 1,000. Let's see what that number is. Well, the sine, that'll be squared here, right? What's that number squared divided by 4 times 1,000, or 4,000? Negative 0.0696 squared. Don't forget to square it, because that's squared, divided by 4,000. Negative. That can't be negative, it's positive, right? We square it. There's no way that would be a negative. That's a positive. The resistor is going to absorb the power. 1.211, it says times 10 to the minus 6. That means micro watts. 10 to the minus 6, 10 to the minus 6 is a micro. So that's why it's a microwatts. That's how much power was absorbed by the load. So now we know how to calculate the maximum power transfer and what value of R sub L will give me a maximum power transfer.